This is problem 2.123. It's on page 75. A container of weight W is suspended from ring A. Cable BAC passes through the ring and is attached to fixed supports at B and C. Two forces, P equals PI and Q equals QK, are applied to the ring to maintain the container in the position shown. Knowing the weight is 270 pounds, determine P. And then there's a hint that the tension in both portions of the cable is the same. In other words, that cable passes through the ring, but the ring is frictionless. So the tension in BA and AC, or AB and AC if you like, is the same. Now the figure is in 3 dimensions. It's a little bit complicated, so I don't think I'm going to draw it. It seems that Q lies along axis Z, even though the figure doesn't really look like it. So if you're looking at the book, it looks like they didn't draw Q very well. It should be parallel to axis Z. That's what the problem statement says. It's pretty obvious that P is only along the X direction though. Now notice that the bucket is not beneath a line between B and C, as it would be if only, if there was no horizontal component of force on the bucket. So unfortunately you'll have to refer to figure P 2.123. But what they said is that the vector Q is the magnitude Q times direction K, and the vector P, that force vector, is P along the I direction. Weight is 270 pounds, and then the tension in AB equals the tension in AC. So again, refer to the figure. We're supposed to find P and Q. Now what I did is I said, I'd like to know the distance between A and B. So that's pretty easy. Just take the lengths from A to B along the coordinate directions, square root of the sum of the squares, and you've got it. So we've got 16, looks like 48 and 72. So 16 squared, 48 squared, and 72 squared. Of course, this is a made-up problem, so that comes out nicely to 88. That means then that the tension in AB as a vector would be whatever the magnitude of that tension is, multiplied by the direction defined by these numbers. Now the 48 would be a negative 48 in the I direction, because of course I'm going, let's see, how did I do that? 48, I'm going from A to B, so I had to move in the negative direction. So from A to B, which makes sense because the tension has to be pointed from A towards B. So negative 48 minus 72J minus 16K, and all of this is over the magnitude of that vector 88. So this is our dx, our dy, dz, and then the magnitude d that the textbook uses. That's their terminology. We can do something similar with AC and find its length as 24 squared plus 72 squared plus 13 squared. Notice I'm not bothering with negative signs. This comes out nicely to 77. Again, I don't care about the units. I don't know. I guess these are inches. That's fine. We've got inches in the numerator, inches in the denominator, so no units. Anyway, then the tension in AC is the magnitude of whatever that tension force is. I don't know what it is yet. And all I need is the directionality at this point. So 24I plus 72J minus 13K. And notice I'm moving, of course, from A to C. Now, we've got components of all of these forces. We don't know what the tension is in AB or AC, but we do know that these two numbers are the same because we're told that the tension in the AB section equals the tension in the AC section. So if we sum forces in the Y direction, is that the Y direction? Yes, in the Y direction, we'll have negative weight, the weight of the bucket pulling down, plus TAC in the Y direction, plus TBC in the Y direction, and this has to sum to 0. Not BC, pardon me. It's AC and AB. There we go. Okay. All right. Well, the weight is negative 270 pounds. This has to come up to 0. Plus TAC. Well, we don't know what TAC is. But to get the Y component of AC, we need 72 over 77. TAB To get its y component, we need negative, I didn't expect that to be negative. Let me look at the problem again. Yeah, that should be positive. What have I done wrong here? AB, yeah, I've made a mistake. My mistake is that I'm not copying my solution that I wrote out. This should be positive, I apologize. So we move in the negative direction, I, but positive direction is J. Well, that makes sense because A is below both B and C. So the Y components should both be positive. Anyway, fixing that little snafu, the AB component, or the Y component of AB should be, what, 72 over 88 of TAB. But we know that these two are the same, so we can write that 270 equals the tension, factoring these two out since they're the same, times 72 over 77 plus 72 over 88. So from this we can get the tension. Just take whatever the number this is, under 270. That'll tell us our result. Now, yeah, so here's where I did it. There we go. So the tension in the ropes then is 154 cables, whatever they are, 154 pounds. Okay. That's not what they asked for. We just need that tension in order to determine P and Q. Notice that this sum of forces has no P or Q in it because P and Q are only in the I and K directions respectively, not in the J direction. Now, in order to find the amount of force P that's required to maintain static equilibrium, let's sum forces in the horizontal direction, the X direction, one of the horizontal directions. In the X direction, we're going to have P in the I direction plus the tension times, and oh, I've just erased the vectors. I apologize, you'll have to rewind the video if you want to see where I'm getting these from. So all I'm doing is reading off the I components. So for, here, let's do it this way. So I need tension in the A, from the AB vector in the X direction, and tension from the AC vector in the X direction. That should sum to 0 because those are the only forces in the X direction. So 0 equals P times, or plus, TAB, and the horizontal component of AB is a negative component, negative 48 over 88. Because AB, from A to B, points in the negative X direction partially, plus tension AC multiplied by, now AC has a positive X component, so 24 over 77. You'll have to look at the I components of those two vectors to see what I'm doing here. Now, if I put P on one side and these on the other, I can factor out the tension. Notice what I'm doing is taking these terms to the other side, and I would have 48 over 88 plus 20, well, no, minus 24 over 77, because I moved this term to the other side as well. Now, since I know the value of the tension in the rope at 154 pounds, I can say then that the force P must be 36 pounds, just solving that. Okay, just multiply 154 times those difference of fractions. And so that means that this is 36I pounds force. That's P. Summing the forces in the vertical, or not vertical, the other horizontal direction, Z, I should also get 0. But in the Z direction, I've got Q acting, plus I've got the tension in AB in the K direction, so we call that Z, plus the tension AC in the Z direction. Now, the tensions are the same, so I'm just going to write T. And in AB, the Z component, or the K component, is negative 16 over 88. But for AC, well, it's also in the negative Z direction, is negative 13 over 77. Okay? So Q is equal to T times the sum of these two. All I'm doing is taking these to the other side, so their sign changes. So 16 over 88 plus 13 over 77. Again, I know the tension is 154 pounds, so Q has magnitude of 54 pounds. Therefore, this vector is 54. Probably should have done it this way. That's better. 54 K pounds force. So there's the magnitude and direction of forces P and Q.